Welcome to Science for Sleep, where we explore the deepest mysteries of our universe in a way that calms the mind and invites peaceful rest. I'm so glad you've chosen to spend this time with us tonight, and I want you to get comfortable, perhaps dim the lights, settle into your favorite position, and prepare for a journey that will gently challenge everything you thought you knew about one of the most fundamental aspects of existence. Tonight, we will drift through the strange and beautiful reality of time dilation, exploring how a series of elegant experiments shattered our conception of time and revealed that the universe is far stranger and more wonderful than common sense could ever suggest. We will walk together through the historical moments when scientists realized that time itself, that constant companion of every moment of your life, is not actually constant at all. We will discover how clocks can tick at different rates depending on how fast they are moving or how deep they sit in a gravitational field. And we will see how this isn't just abstract theory, but verified reality that shapes the technology in your pocket right now. Before we begin this exploration, I want to ask you something, and I'd love for you to share your thoughts in the comments below. Have you ever wondered if time passes the same for everyone, everywhere in the universe? Does a second on Earth equal a second on a distant star, or near a black hole, or aboard a spaceship traveling close to the speed of light? What does your intuition tell you? Take a moment to consider this, and please share your initial thoughts in the comments. There are no wrong answers here, only the honest sense we all have about how reality should work. And it's that very sense that we're going to gently expand tonight. If you enjoy content that combines rigorous science with a peaceful, contemplative atmosphere perfect for rest and reflection, please take a moment to like this video and subscribe to Science for Sleep. Your support helps us create more of these long-form explorations where we can really take our time. Tonight's exploration will take us from the ancient world, where time seemed as steady as the rising sun, through the scientific revolutions that revealed time's hidden flexibility, to the precise experiments that proved beyond doubt that time dilation is real. We'll see atomic clocks flown around the world on passenger jets, measuring time differences of mere nanoseconds that perfectly matched Einstein's predictions. We'll discover why particles from space called muons shouldn't be able to reach Earth's surface, but do anyway, because time slows down for them as they race through the atmosphere. We'll understand why the global positioning system in your phone has to constantly correct for time dilation, or else your navigation would become hopelessly inaccurate within minutes. And we'll contemplate what all of this means for our understanding of reality, for the nature of past and present and future, for the very fabric of the cosmos we call home. So breathe deeply, let your mind open to possibility, and join me as we step outside the common sense world and into the tested, verified, beautifully strange reality that physics has revealed. The journey begins now. Time feels like the most basic, most obviously true aspect of existence. It flows from past through present into future at a steady, unchanging rate. A minute is a minute, whether you experience it on a mountaintop or in a valley, whether you're sitting still or racing in a jet, whether you are on Earth or would somehow be transported to Mars or Jupiter or the edge of the galaxy. This intuition, this deep sense that time is universal and absolute, is so fundamental to human experience that for most of history it was never even questioned. It simply was the background against which all events unfolded, the stage upon which the play of existence was performed, itself unchanging and uniform. Our ancestors looked at the sky and saw the sun rise and set with regularity that became the foundation of timekeeping, saw the moon cycle through its phases, saw the seasons turn in their eternal dance. And from these observations came the very concept of time as something that could be measured and marked and divided into useful units. The ancient civilizations developed increasingly sophisticated ways to track time's passage, recognizing its importance for agriculture, for religious observances, for coordinating human activity. The Babylonians divided the day into 12 double hours and developed water clocks called clepsydra that measured time by the steady drip of water from one vessel to another. The Egyptians used shadow clocks and obelisks, watching how shadows moved across marked surfaces as the sun traversed the sky, creating some of the earliest sundials. These devices embodied the assumption that time itself was flowing at a constant rate, and that human cleverness could mark that flow with increasing precision. The water dripped steadily, the shadows moved predictably, the celestial bodies wheeled overhead with clockwork regularity, and all of this reinforced the belief that time was an absolute backdrop, the same everywhere and for everyone. As civilizations advanced, so did timekeeping technology, but the fundamental conception remained unchanged. Medieval monks developed mechanical clocks to regulate prayer times, clocks driven by falling weights that turned gears with carefully calculated ratios to move hands around a face marked with hours and minutes. These mechanical marvels, growing ever more accurate through the Renaissance and into the Industrial Age, I seem to be measuring something objective and real, something external to human perception. When a clock said it was noon, it was noon. And if you had another clock properly synchronized with the first, it would also say noon. And this seemed self-evident and unchallengeable. Time was like a river flowing at constant speed, and clocks were merely our instruments for measuring how far along that river we had traveled. This intuitive understanding of time reached its most sophisticated pre-Einstein formulation in the work of Isaac Newton, whose Principia Mathematica, published in 1687, laid out the laws of motion and gravitation that would dominate physics for more than 200 years. Newton explicitly defined what he called absolute time, writing that absolute, true, and mathematical time of itself, and from its own nature, flows equably without relation to anything external. This was Newton's formal statement of what everyone already believed, that time has its own existence, independent of events, independent of observers, independent of anything happening within it. It flows uniformly at the same rate everywhere in the universe, providing a universal standard against which all motion and change could be measured. If something happened at a particular moment in absolute time, that moment was the same for all observers everywhere, regardless of their motion or position. There was a universal now that extended across all of space, a cosmic present moment that everyone shared. Newton's physics was extraordinarily successful. so successful that it became not just a theory, but seemed to be the revealed truth about how nature worked. His laws predicted planetary motions with stunning accuracy, explained the tides, guided the design of machines and structures, and formed the foundation for the entire scientific revolution that transformed human civilization. And woven into this success was the assumption of absolute time that ticked away uniformly whether stars were being born or exploding, whether planets orbited or collided, whether life arose or went extinct. The universe operated like a vast machine, and time was the parameter that marked the machine's operation, external to the machine itself and unaffected by anything the machine did. This conception was so deeply embedded in physics that questioning it seemed almost meaningless, like questioning whether up was different from down or whether circles were round. But there were hints, subtle and easily missed, that something was not quite right with this picture. As physics became more precise, as experiments probed nature at smaller scales and higher speeds, small discrepancies began to appear, anomalies that didn't quite fit the neat Newtonian framework. The behavior of light, in particular, seemed strange in ways that would eventually crack the edifice of absolute time. But we are getting ahead of ourselves. For now, it is important to understand just how natural and obvious the old conception of time was, how it matched every aspect of daily human experience, how it required no special thought or consideration, because it was simply the way things were. When you walked from one place to another, time passed at the same rate for you as for someone standing still. When you rode a horse, or later a train, time continued its steady flow, unaffected by your motion. The clock in your pocket, and the clock on the wall, and the sun in the sky all agreed about what time it was, and this agreement seemed to prove that time was absolute and universal. Our human perception of time also contributed to this belief in its constancy. We experience time psychologically, and that experience can vary tremendously. A moment of terror can seem to stretch out endlessly, while hours of enjoyment can flash by in what feels like minutes. Waiting for important news makes time crawl, while absorbed in fascinating work makes it fly. But even as we experienced these psychological variations, we knew they were subjective, that when we emerged from our subjective experience and checked a clock, we would find that objective time had continued its steady march, regardless of how we had experienced it. The clock was the arbiter of reality, showing us that beneath our variable perceptions, there was an objective time that we could trust and measure and use to coordinate our activities with others. This distinction between subjective time perception and objective time measurement seemed to prove that real time existed outside of minds and perceptions, that it was a feature of the universe itself. Philosophers debated the nature of time, asking whether it was a thing in itself or merely a relation between events, whether the past and future were real or only the present moment existed, whether time had a beginning or stretched infinitely into the past. These were deep questions, but almost all philosophers agreed that whatever time was, it flowed at the same rate for all observers. Kant argued that time was a form of human intuition, a way our mind structured experience rather than a feature of external reality. But even this idealist position maintained that time's rate was uniform and absolute within human experience. The debate was about time's metaphysical status, not about whether it could flow at different rates in different circumstances. That possibility simply wasn't on anyone's radar, wasn't conceivable within the framework of thought that had developed over millennia of human reflection and observation. So, as we approach the dawn of the 20th century, we find physics at a peculiar juncture. Newton's laws had proven spectacularly successful for over 200 years. They sent spacecraft to the moon and back with extraordinary precision. They predicted eclipses centuries in advance. They explained the mechanical world from pendulums to planets. The concept of absolute time was so embedded in this success that questioning it seemed to be questioning reality itself. Engineers and physicists used Newtonian mechanics every day with complete confidence, and it worked. It gave right answers. It matched observations and predictions to high precision. And yet, there were puzzles emerging, problems that didn't quite fit, observations that were just slightly off from what the theory predicted. Most physicists assumed these were minor issues that would be resolved with better measurements or small modifications to the theory, tweaks that would preserve the essential framework while accounting for edge cases. Almost no one suspected that the entire edifice was about to be revolutionized, that the seemingly obvious and universal nature of time was about to be revealed as an illusion, a local approximation that breaks down when we look carefully at the universe's actual behavior. The stage was set for one of the greatest intellectual revolutions in human history, though few yet realized that the play was about to begin. The story of how time dilation was discovered begins not with time, but with light, that most familiar yet mysterious phenomenon that allows us to see the world around us. Light seemed simple enough. It traveled in straight lines. It bounced off mirrors in predictable ways. It could be split into colors with prisms, and it definitely had a speed, a finite velocity at which it propagated through space. But measuring that speed proved remarkably difficult, and when scientists finally succeeded in measuring it with precision, they discovered something that would eventually overturn our entire understanding of space and time. The journey to this discovery was long and filled with failed experiments, puzzling results, and conclusions that seemed impossible, yet kept being confirmed by ever more precise measurements. Let us trace this path, walking through the attempts to understand light that would ultimately reveal the flexibility of time itself. The first serious attempt to measure the speed of light was made by Galileo Galilei around 1638, using a method that seems charmingly simple, but was ultimately inadequate to the task. Galileo stationed two observers on hilltops about a mile apart at night, each with a lantern that could be covered and uncovered. The first observer would uncover his lantern, and as soon as the second observer saw the light, he would uncover his own lantern. By measuring the time between the first observer uncovering his lantern and seeing the response from the second observer, Galileo hoped to measure how long light took to travel the 2-mile round trip between the hills. The experiment failed because human reaction time was far longer than the time light took to cover such a short distance. Light travels so fast that it covers 1 mile in about 5 microseconds, far too quick for human reflexes to measure. Galileo concluded that light either traveled instantaneously or so fast that its speed was immeasurable by his methods, and he moved on to other problems. But the question remained hanging in the air, to waiting for better technology and cleverer methods. The first successful measurement of light speed came from an unexpected source, the careful observation of the moons of Jupiter. In 1676, Danish astronomer Ole Rømer was studying the orbits of Jupiter's moons, particularly Io, the innermost large moon that orbits Jupiter every 42.5 hours. Rømer noticed something peculiar. When Earth was moving toward Jupiter in its orbit, the eclipses of Io appeared to happen slightly earlier than predicted. When Earth was moving away from Jupiter 6 months later, the eclipses appeared to happen slightly later than predicted. The total discrepancy over Earth's orbit amounted to about 22 minutes. Rømer realized that this delay was not due to any irregularity in Io's orbit, but rather to the changing distance that light had to travel from Jupiter to Earth. When Earth was closer to Jupiter, light from Io's eclipses had less distance to travel and arrived sooner. When Earth was farther away, light had more distance to travel and arrived later. By calculating the difference in Earth's distance from Jupiter between the two observations and dividing by the time difference, Rømer obtained the first rough estimate of light speed, about 220,000 kilometers per second, remarkably close to the true value considering the uncertainties in measuring interplanetary distances at that time. Over the next 2 centuries, increasingly sophisticated experiments refined the measurement of light speed. In 1849, French physicist Hippolyte Fizeau used a rapidly rotating toothed wheel to measure light speed over terrestrial distances. He shone light through the gaps between the teeth of the wheel, and the light traveled to a distant mirror and back. By adjusting the wheel's rotation speed until the returning light was blocked by a tooth rather than passing through a gap, Fizeau could calculate how long the light had been traveling and thus determine its speed. His result was about 315,000 kilometers per second, again remarkably good for the technology available. These and similar experiments all converged on a value around 300,000 kilometers per second, or about 186,000 miles per second, a speed so vast that light could circle the Earth more than 7 times in a single second, yet still finite and measurable. But as these measurements improved, physicists began to encounter a profound puzzle. According to Newton's physics, velocities should be additive. If you are on a train moving 30 miles per hour and you throw a ball forward at 20 miles per hour relative to the train, someone standing beside the tracks would measure the ball's speed as 50 miles per hour, the sum of the train speed and your throwing speed. This seemed obvious and was confirmed by every everyday experience. But what about light? If light travels at 300,000 kilometers per second, and you are on a spaceship moving at 100,000 kilometers per second in the same direction as a light beam, shouldn't you measure the light as moving at only 200,000 kilometers per second relative to you? And if you were moving toward an approaching light beam at 100,000 kilometers per second, shouldn't you measure that beam as approaching at 400,000 kilometers per second? According to Newtonian physics and common sense, the answer should be yes. But nature, it turned out, had other ideas. The puzzle deepened when physicists considered the medium through which light waves were thought to propagate. Sound waves need air or water or some material medium to travel through. Ocean waves need water. Earthquake waves need solid ground. It seemed natural to assume that light waves also needed some medium, and physicists postulated the existence of a substance called the luminiferous ether, an invisible, weightless, a perfectly transparent substance that filled all of space and through which light waves propagated like ripples on a pond. The ether was thought to be the absolute reference frame, the true standard of rest against which all motion could be measured. If the ether existed, then light should travel at 300,000 kilometers per second relative to the ether, and objects moving through the ether should measure different light speeds depending on their motion through this absolute medium. Earth orbits the Sun at about 30 kilometers per second. So as Earth moves through the ether, we should be able to detect an ether wind, a change in the measured speed of light, depending on whether we measure it in the direction of Earth's motion or perpendicular to it. In 1887, American physicists Albert Michelson and Edward Morley performed what would become the most famous failed experiment in the history of science. They built an exquisitely sensitive device called an interferometer that could detect tiny differences in the speed of light traveling in different directions. The device split a beam of light into two perpendicular beams, sent them along paths of equal length, and then recombined them. If light traveled at different speeds along the two paths due to Earth's motion through the ether, the light waves would arrive at slightly different times and would interfere with each other in a detectable pattern. Michelson and Morley calculated that the ether wind from Earth's orbital motion should produce an easily measurable effect in their apparatus. They performed their experiment with meticulous care, rotating their apparatus to measure light speed in every direction, repeating their measurements at different times of day and different seasons of the year to account for Earth's rotation and orbit. The result was stunning and completely unexpected. They found nothing. No ether wind. No difference in light's speed, regardless of the direction measured. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. At first, this null result was seen as a puzzle to be explained within the existing framework of physics. Perhaps Earth dragged the ether along with it, so we were always at rest relative to the local ether. Perhaps the ether had strange properties that compensated for Earth's motion in ways that made the motion undetectable. Physicists, including George Fitzgerald and Hendrik Lorentz, proposed that objects moving through the ether actually contracted along their direction of motion by just enough to compensate for the expected ether wind effect, making the motion undetectable. These explanations were ingenious, but ultimately unsatisfying because they seemed contrived, like adding epicycles to save a theory that nature was telling us was wrong. The experimental results kept refusing to show any evidence of ether or of relative motion affecting the speed of light. Light stubbornly traveled at the same speed in every direction for every observer, a fact that seemed to violate basic common sense and Newtonian physics, but that kept being verified by experiment after experiment. Into this confused situation stepped a young Albert Einstein, who in 1905 was working as a patent examiner in Bern, Switzerland, spending his days evaluating patent applications and his spare time thinking deeply about the fundamental problems in physics. Einstein approached the light speed problem from a radically different angle than his contemporaries. Rather than trying to explain away the Michelson-Morley null result or to salvage the ether hypothesis, Einstein asked what would follow if we simply accepted the experimental fact at face value. What if light really does travel at the same speed for all observers, regardless of their motion? What if this is not a problem to be explained away, but rather a fundamental principle of nature that we should accept and build our theory around? This question led Einstein to one of the most revolutionary papers in the history of science, his 1905 publication on the electrodynamics of moving bodies, which introduced what we now call special relativity. Einstein based his theory on two postulates, two principles that he took as starting points, without trying to derive them from anything more fundamental. The first postulate was the principle of relativity, which stated that the laws of physics are the same in all inertial reference frames, meaning that there is no absolute state of rest and no experiment you can perform inside a sealed laboratory moving at constant velocity that will tell you whether you are moving or stationary. This principle was not new. It went back to Galileo and was implicit in Newtonian mechanics, though Newton's assumption of absolute time had obscured its full implications. The second postulate was the constancy of the speed of light. The assertion that light travels at the same speed, approximately 300,000 kilometers per second, for all observers, regardless of their motion or the motion of the light source. This second postulate was the radical one, the one that flew in the face of common sense and Newtonian velocity addition, the one that forced a complete reconceptualization of space and time. Einstein realized that if light's speed is constant for all observers, then something else must be flexible to accommodate this constancy. In Newtonian physics, time is absolute and space is absolute, so velocities simply add and subtract according to the motion of the observer. But if light's velocity doesn't add or subtract with observer motion, if it remains stubbornly constant, then either space or time or both must be relative rather than absolute. Different observers moving at different speeds must experience space and time differently in just such a way that they all measure the same speed for light. This was the revolutionary insight that led to time dilation and length contraction, and all the other strange predictions of special relativity. To maintain the constancy of light speed, nature had to make time itself flexible, had to allow clocks moving at different speeds to tick at different rates, had to abandon the universal now that Newton had assumed and that common sense seemed to require. The logic was inescapable once you accepted the constancy of light speed. Imagine you are on a train moving very fast, and you shine a flashlight forward along the train. You measure the light traveling at 300,000 kilometers per second relative to you, but someone standing beside the tracks watches this same light beam. And according to Einstein's second postulate, They also must measure it traveling at 300,000 kilometers per second relative to them. Not faster, even though the train is moving in the same direction as the light. How can both measurements be correct? The only way is if time itself is passing at different rates for you on the train and for the observer on the ground. Your clock must be ticking slower than the ground observer's clock, and your measuring stick must be contracted in just such proportions that your measurement of light's speed and the ground observer's measurement of the same light give identical results despite your relative motion. This is time dilation, and it is not an illusion or a measurement error or a trick of perception. It is a real physical difference in the rate at which time passes for observers in relative motion. Einstein worked out the mathematics of this new understanding of space and time, deriving what are now called the Lorentz transformations, equations that tell you exactly how to translate measurements of time and space from one reference frame to another, moving at constant velocity relative to the first. These equations showed that time dilation becomes more pronounced as relative velocity increases, and becomes extreme as velocity approaches the speed of light. At everyday speeds, even the speed of jet aircraft or rockets, the time dilation effect is tiny, measured in nanoseconds or microseconds, far too small to notice without atomic clocks. This is why we never noticed time dilation in our daily experience. Why it seemed obvious that time was absolute. We were living in the slow speed approximation where Newton's physics works perfectly well. But at speeds approaching the speed of light, time dilation becomes dramatic, with moving clocks ticking slower and slower until at the speed of light itself. If it could be reached, time would stop entirely. This was a universe stranger than anyone had imagined. A universe where time itself bent and flexed to preserve the cosmic speed limit of light. The scientific community's reaction to Einstein's special relativity was initially mixed. Some recognized immediately that this was a work of genius that solved long-standing puzzles and revealed deep truths about nature. Others were skeptical, finding the ideas too radical, too contrary to common sense and to the successful Newtonian framework that had served science so well for centuries. But Einstein's theory made predictions, specific quantitative predictions that could be tested by experiment. And as those experiments were performed over the coming decades, special relativity was confirmed again and again with increasing precision. Time dilation was not just a theoretical curiosity, but a real phenomenon that nature exhibited whenever careful enough measurements were made. The experiments that proved this, that took Einstein's abstract mathematics and showed it to be concrete reality, are among the most elegant and important experiments in the history of science. And it is to these experiments that we now turn our attention, leaving behind the world of thought and entering the world of clocks and aircraft and particles and precision measurement that would verify beyond doubt that time is relative. To understand time dilation, we need to think carefully about what we mean by time and how we measure it. At its most basic, time is what clocks measure, and a clock is any physical process that repeats regularly, allowing us to count cycles and mark the passage of time. The rotation of the Earth is a clock, giving us days. The orbit of Earth around the Sun is a clock, giving us years. The swing of a pendulum is a clock. The vibration of a quartz crystal is a clock. The oscillation of light waves between two mirrors is a clock. And at the most fundamental level, the vibration of atoms is a clock, which is how modern atomic clocks achieve their extraordinary precision. When we say that time dilates, what we mean specifically is that these physical processes, these natural clocks, actually tick at different rates depending on their motion or their position in a gravitational field. This is not a defect in the clocks, but a feature of time itself, and all clocks slow down together, including biological processes, radioactive decay, and every other time-dependent phenomenon. Einstein used a beautiful thought experiment to help understand time dilation, an imaginary device called a light clock. Picture a clock that consists of two mirrors facing each other, separated by some distance, say 1 meter. A pulse of light bounces back and forth between these mirrors, and each round trip of the light constitutes one tick of the clock. If the mirrors are 1 meter apart and light travels at 300,000 kilometers per second, then each tick takes about 6 nanoseconds. But the actual numbers don't matter for understanding the principle. Now, imagine you are holding this light clock and you are at rest, or rather, you consider yourself at rest, which is all that matters in relativity, since there is no absolute rest. You watch the light pulse bounce up and down between the mirrors, and you count ticks. Each tick takes the same amount of time, and this is your measurement of time passing. Now, imagine I am watching you go by at very high speed, holding your light clock. From my perspective, your light clock is moving, which means that the light pulse inside it is not simply bouncing straight up and down between the mirrors. Instead, as the light travels from the bottom mirror to the top mirror, the entire clock moves forward. So, from my point of view, the light has to travel at an angle to catch up with the top mirror, which has moved during the light's flight time. The light path from my perspective is thus longer than the light path from your perspective. The light has to travel diagonally rather than straight up and down. But here is the crucial point. The speed of light must be the same for both of us. This is Einstein's second postulate, the constancy of light speed. If the light travels a longer distance from my perspective but at the same speed, then it must take more time from my perspective to complete one tick. Your clock appears to me to be ticking slower than an identical clock that I am holding, and that is at rest relative to me. This is time dilation explained through the light clock thought experiment. The moving clock ticks slower, not because there is something wrong with it, but because the geometry of light's path is different for different observers. And since light speed must be constant, time itself must adjust to accommodate this geometric difference. And crucially, this is not just about light clocks. Every clock moving with you, including your heartbeat, your watch, your cellular metabolism, your thoughts, everything time-dependent, slows down by exactly the same factor as the light clock. If your light clock appears to me to tick at half speed, then your watch appears to tick at half speed. You appear to age at half speed. Radioactive atoms traveling with you appear to decay at half speed. Time itself, for you, is passing more slowly from my perspective. But from your perspective, you notice nothing unusual at all. Your clocks all tick normally. You age normally, your thoughts proceed normally, because all your clocks have slowed down together. You have no way to detect that time is passing more slowly for you because you have nothing to compare it to within your reference frame. The mathematics of time dilation is captured in what is called the Lorentz factor, usually denoted by the Greek letter gamma. The formula is gamma equals 1 divided by the square root of 1 minus v squared divided by c squared, where v is the relative velocity between two observers and c is the speed of light. When v is much smaller than c, which is the case for all ordinary speeds, gamma is very close to 1, meaning there is almost no time dilation. A car moving at 100 kilometers per hour has a gamma factor that differs from 1 by less than 1 part in 10 to the 16th power, utterly negligible. Even a spacecraft moving at 11 kilometers per second, the escape velocity from Earth, has a gamma factor that differs from 1 by only about 1 part in 1 trillion, still too small to measure with ordinary clocks. But as v approaches c, gamma grows rapidly toward infinity. At 90% of light speed, gamma is about 2.3, meaning that moving clocks tick at only about 43% of the rate of stationary clocks. At 99% of light speed, gamma is about 7, meaning moving clocks tick at 1/7 speed. At 99.9% of light speed, gamma is about 22, and time dilation becomes dramatic. One of the most famous illustrations of time dilation is the twin paradox, which is not actually a paradox, but rather a profound demonstration of how time dilation works in special relativity. Imagine twins. One stays on Earth while the other travels on a spacecraft to a distant star and returns. The traveling twins' journey is at very high speed, say 90% of light speed, and the star is, say, 20 light-years away. From Earth's perspective, the round trip takes about 44 years, accounting for the time to accelerate and decelerate, and the travel time at high speed. The twin on Earth ages 44 years during this time. But the traveling twin, moving at high speed for most of the journey, experiences time dilation. Their clock ticks slower, and from Earth's perspective, they age more slowly. When the traveling twin returns to Earth, they have aged only about 20 years, having experienced less time than their earthbound sibling. The traveling twin is now 24 years younger than their twin, not because of anything magical, but simply because less time actually passed for them during their high-speed journey. The so-called paradox arises when people ask, from the traveling twin's perspective, isn't the Earth moving away at high speed and then returning? So shouldn't the Earth twin be the one who ages less? This seems to create a contradiction where each twin should be younger than the other, which is impossible. The resolution is that the situation is not actually symmetrical. The traveling twin accelerates to leave Earth, turns around at the distant star, and accelerates again to return, experiencing forces during these acceleration phases. The Earth twin remains in an inertial reference frame, meaning they don't accelerate. Special relativity applies to inertial frames moving at constant velocity, and the full analysis of the twin paradox requires considering the acceleration phases, which breaks the symmetry between the twins. When you do the full calculation properly, both twins agree on which one is younger when they reunite, and it is always the traveling twin who has aged less. There is no actual paradox, just a deep truth about how time behaves for objects in motion. Time dilation has another important consequence called the relativity of simultaneity, which means that events that appear simultaneous to one observer may not appear simultaneous to another observer in motion relative to the first. Imagine two lightning strikes hitting opposite ends of a moving train at the same moment, according to someone standing beside the tracks. To that observer, the light from both strikes reaches their eyes at the same time if they are standing at the midpoint between the strikes. So they conclude the strikes were simultaneous. But someone standing at the center of the moving train will see the light from the strike at the front of the train first, because the train is moving toward that light, and will see the light from the rear strike later because the train is moving away from that light. Since light speed is the same for all observers, the passenger on the train must conclude that the front strike happened first and the rear strike happened later. The strikes that were simultaneous in one reference frame are not simultaneous in another reference frame moving relative to the first. This relativity of simultaneity undermines the concept of a universal now, a single present moment shared by all observers everywhere. In Newtonian physics with absolute time, there was a cosmic present, a moment that was now for everyone and everything in the universe, regardless of location or motion. But relativity shows that there is no such universal present. What is simultaneous for one observer is not simultaneous for another, and there is no way to say which observer is correct because both are equally valid. This has profound philosophical implications about the nature of time and about whether the past and future are real. If different observers disagree about which events are happening now, then in what sense does the present exist as something objective? These questions lead into deep waters of philosophy of time that we will explore more later. But for now, the key point is that time dilation is not just about clocks ticking at different rates, but about the entire structure of space and time being relative to the observer. Einstein's special relativity also reveals that space and time are not separate independent entities, but are woven together into a four-dimensional fabric called space-time. An event in space-time has four coordinates, 3 of space and 1 of time. Different observers moving at different velocities slice through this four-dimensional space-time at different angles, so to speak, which is why they disagree about measurements of time and space separately, but agree on certain combinations of space and time called space-time intervals. The mathematics of special relativity treats space and time together in what is called Minkowski spacetime, named after mathematician Hermann Minkowski, who developed this geometric interpretation of Einstein's theory. In this view, time dilation and length contraction are two aspects of the same phenomenon, the rotation of reference frames in spacetime. Just as in ordinary space you can rotate your coordinates so that what was distance in the x direction becomes partly distance in the y direction. The implications of time dilation become particularly striking when we consider what happens as velocity approaches the speed of light. The Lorentz factor gamma grows without bound as velocity approaches c, meaning that time dilation becomes extreme. At 99.99% of light speed, gamma is about 70, meaning a moving clock ticks at only about 1.4% of the rate of a stationary clock. At this speed, a journey that takes 70 years from Earth's perspective would take only 1 year from the traveler's perspective. In principle, a traveler could reach distant stars in their own lifetime, even though the journey takes many Earth years, because their time is so dilated. This means that time dilation offers a kind of one-way time travel to the future. The traveler ages slowly relative to the rest of the universe and arrives at their destination to find that far more time has passed for everyone else than for them, and they have effectively traveled into the future, not by moving through time directly, but by slowing their own clock relative to the clocks of others. But there is a fundamental limit in special relativity that prevents any object with mass from reaching the speed of light. As an object accelerates and approaches light speed, its energy increases, and according to relativity, its mass effectively increases as well, in a sense that the force needed to accelerate it further grows without bound. To actually reach the speed of light would require infinite energy, which is impossible. Light itself can travel at light speed because photons are massless particles, and it is precisely because they have no mass that they must travel at the cosmic speed limit. But anything with mass, no matter how much energy you give it, I can only approach but never quite reach the speed of light. This speed limit is not arbitrary, but follows from the same postulates that give us time dilation. The constancy of light speed and the principle that physics is the same in all inertial frames together imply that there must be a maximum possible velocity, and that velocity is c, the speed of light. Nothing can travel faster, not because we lack sufficient technology, but because the structure of space-time itself forbids it. Time dilation thus sits at the heart of Einstein's special relativity, a consequence of the constancy of light speed and the relativity of motion. It transforms time from an absolute universal flow into something relative and flexible, different for different observers in different states of motion. And remarkably, this strange prediction of the theory is not just mathematical abstraction, but is testable, verifiable, observable reality. Over the past century, physicists have performed increasingly precise experiments that demonstrate time dilation in exactly the way Einstein predicted. These experiments take the thought experiments and make them real, building actual light clocks or using natural clocks like particle decay or atomic vibrations, and showing that moving clocks really do tick slower. It is to these experimental confirmations that we now turn, seeing how abstract theory became concrete fact through the patient, careful work of experimental physics testing nature, and finding that nature agrees with relativity to extraordinary precision. If you're finding this exploration of time dilation fascinating, and if this gentle journey through one of physics' most profound discoveries is helping you drift toward restful sleep while expanding your mind, please consider subscribing to Science for Sleep. We create these detailed, carefully paced explorations specifically for people who love learning but also need to calm their thoughts at the end of the day. Your subscription helps us continue producing this unique content where science and sleep meet. And please do like this video and share your thoughts in the comments about how these revelations about time make you feel about reality? Are you surprised, fascinated, unsettled? We'd love to hear from you. Einstein's special relativity, published in 1905, was a brilliant theoretical achievement that solved long-standing puzzles about light and electromagnetism, while revealing that space and time are not what they seem. But physics is an empirical science, and beautiful theories must ultimately be tested against reality through experiment and observation. The predictions of special relativity, particularly time dilation, were so contrary to everyday experience and common sense that they demanded rigorous experimental verification. Over the decades following Einstein's work, physicists designed and performed increasingly sophisticated experiments to test whether time really does dilate as relativity predicts. Every experiment, without exception, has confirmed that time dilation is real. The effects are small at ordinary velocities, but they are measurable with precise enough instruments. And at high velocities or in strong gravitational fields, time dilation becomes dramatic and unmistakable. Let us walk through the most important of these experiments, seeing how patient observation and clever experimental design proved that time truly is relative. Perhaps the most elegant and widely known direct test of time dilation was performed in October 1971 by physicists Joseph Haffel and Richard Keating. Their experiment was beautifully simple in concept, though complex in execution. They took 4 cesium beam atomic clocks, some of the most precise timekeepers available at the time, and flew them around the world on commercial passenger jets, while comparing their readings to reference atomic clocks that remained at the United States Naval Observatory in Washington, D.C. The experiment tested both special relativistic time dilation due to the velocity of the aircraft and general relativistic time dilation due to the altitude of the flights, effects we will discuss in more detail later. The predictions from relativity were clear and quantitative. Clocks flying eastward with Earth's rotation should lose time compared to the ground clocks, while clocks flying westward against Earth's rotation should gain time, and the predicted differences were small but within the measurement capability of atomic clocks. Atomic clocks are extraordinary devices that measure time based on the oscillation frequency of atoms, typically cesium or rubidium atoms. A cesium atomic clock uses the fact that cesium atoms oscillate between 2 energy states with a precisely defined frequency of 9,192,631,770 cycles per second. This frequency is so stable and reproducible that the second is now defined by international agreement as the duration of 9,192,631,770 of these cesium oscillations. In 1971, the best cesium atomic clocks could measure time with an uncertainty of only a few nanoseconds per day, which made them just barely precise enough to detect the tiny relativistic effects from flying around the world on passenger jets. The challenge was to keep the clock stable and protected during the flights, while recording their readings precisely enough to detect time differences of just tens or hundreds of nanoseconds accumulated over several days of flight time. Haffel and Keating first flew eastward, making a round-the-world trip with stops in various cities, carrying their atomic clocks in passenger aircraft seats and taking elaborate precautions to keep the clocks stable and monitored. Commercial jets fly at about 800 kilometers per hour at an altitude of about 10 kilometers, and the trip took several days, including stops. When they returned to Washington and compared their traveling clocks to the reference clocks that had stayed at the observatory, they found that the traveling clocks had lost time, ticking slower than the reference clocks. The average time loss was 59 nanoseconds, plus or minus 10 nanoseconds, compared to a predicted loss from relativity of 40 nanoseconds. Given the experimental uncertainties in exact flight speeds, altitudes and paths, as well as the precision limits of the clocks, this was excellent agreement between theory and observation. The eastward flying clocks had experienced time dilation. Then Haffel and Keating repeated the experiment flying westward, once again carrying their atomic clocks around the world on commercial aircraft, but this time flying against Earth's rotation. Relativity predicted a different result for westward flight, because the aircraft's velocity relative to the center of Earth would be slower when flying west than when stationary on the ground, since the ground itself is moving eastward with Earth's rotation. In relativity, what matters is not your velocity relative to the ground, but your velocity relative to the non-rotating reference frame centered on Earth. And flying west at jet speed roughly cancels out the eastward velocity from Earth's rotation. The calculation showed that westward flying clocks should actually tick faster than ground clocks, due to their effectively slower motion in the Earth-centered frame, more than compensating for the small slowdown from special relativity due to motion relative to the Earth's surface. Additionally, both eastward and westward flights experience a speed up from general relativistic gravitational time dilation, due to being at higher altitude where gravity is slightly weaker, an effect that adds to the time gain for westward flight and partially cancels the time loss for eastward flight. When Haffel and Keating completed their westward circumnavigation and compared their clocks to the reference clocks, they found that the traveling clocks had gained time, ticking faster than the clocks that stayed on the ground. The average time gain was 273 nanoseconds, plus or minus 7 nanoseconds, compared to a predicted gain of 275 nanoseconds. Once again, the agreement between theory and experiment was excellent. The traveling clocks had measured less time passing than the stationary clocks, exactly as relativity predicted, and the magnitude of the effect matched the theoretical calculation within experimental uncertainty. The Haffel-Keating experiment was a triumph of precision measurement and experimental design, are taking abstract equations and turning them into concrete observations using clocks flying on passenger jets with ordinary travelers sitting nearby, probably unaware that they were participants in one of the most important physics experiments of the 20th century. The results of the Haffel-Keating experiment were published in the journal Science in July 1972 and generated considerable interest in both the scientific community and the public. Here was direct proof that time dilation was real, that clocks in motion actually ticked at different rates than clocks at rest, and that Einstein's predictions were accurate to within experimental error. Skeptics who had thought that time dilation was merely a mathematical artifact or a misinterpretation of observations, now had to confront the fact that real clocks, using atomic physics to measure time, showed exactly the predicted deviations. The experiment has since been repeated with improved technology and has been confirmed to even higher precision, leaving no doubt that time dilation is a real physical phenomenon. Another powerful demonstration of time dilation comes from particles called muons that are created when cosmic rays, high-energy particles from space, collide with atoms in Earth's upper atmosphere. Muons are elementary particles similar to electrons, but about 200 times more massive, and they are unstable, decaying radioactively with a half-life of about 2.2 microseconds when at rest. This means that if you create a collection of muons and watch them, after 2.2 microseconds about half will have decayed into other particles. After another 2.2 microseconds, about half of the remaining muons will have decayed, and so on. The muons decay is a natural clock, ticking away with a well-defined rate that can be measured in laboratory experiments. And because this decay rate is fundamental physics, the same for all muons everywhere, it provides a perfect test of time dilation when muons are moving at high speeds. Cosmic ray collisions in the upper atmosphere at altitudes of about 15 to 20 kilometers create showers of particles, including large numbers of muons. These muons are produced with very high speeds, typically around 98% of the speed of light. Now, here is the puzzle. If muons live for only 2.2 microseconds and travel at nearly the speed of light, they should travel only about 660 meters before half of them decay. Starting at 15 kilometers altitude, the muons would need to survive for about 50 microseconds to reach sea level, which is about 23 muon half-lives. After 23 half-lives, only about 1 muon in 8 million should remain. So we should see essentially no muons at sea level because almost all should have decayed during their journey down through the atmosphere. But observations show something completely different. We detect enormous numbers of muons at sea level, about 1 muon passing through each square centimeter of surface every minute. The flux of muons at sea level is far higher than would be possible if they were decaying at their rest half-life rate during the journey. The explanation is time dilation. From our reference frame on the ground, the muons are moving at 98% of light speed, which gives a gamma factor of about 5. This means that the muons' internal clocks, including their decay processes, are running about 5 times slower than they would at rest. From our perspective, the muons live not 2.2 microseconds, but about 11 microseconds, which is just enough time for them to travel the 15 kilometers from their creation point to sea level before most of them decay. The time dilation exactly accounts for why we observe so many muons at sea level. The muons' radioactive decay is a natural clock, and that clock ticks slower when the muons are moving at high speed, allowing them to survive much longer from our perspective than they would if they were at rest. This is not a matter of interpretation or calculation artifact. The muons really do take longer to decay when they're moving at high speed, and we can count them and measure their decay rate and verify that the effect is exactly what relativity predicts. Interestingly, from the muons' perspective, something different is happening. In the muons reference frame, it is at rest, and the Earth is rushing upward at 98% of light speed. The muon's internal clock runs at its normal rate, and it lives for only 2.2 microseconds in its own frame. So how does the muon reach sea level if it only lives for such a short time? The answer is length contraction, the complementary effect to time dilation. In the muon's reference frame, the 15-kilometer thickness of the atmosphere is contracted by the same gamma factor of 5, appearing to be only about 3 kilometers thick. At 98% of light speed, the muon can traverse this contracted distance in about 10 microseconds of its own time, which is less than 5 muon half-lives, allowing plenty of muons to reach the surface. So, from the muon's perspective, it reaches the surface because the atmosphere is thinner due to length contraction, while from our perspective, the muon reaches the surface because it lives longer due to time dilation. Both explanations are correct in their respective reference frames, and both give the same physical result, that muons are detected at sea level in large numbers. The muon decay experiment has been performed with great precision using particle detectors at different altitudes, measuring the muon flux and energy distribution and comparing it with predictions from relativity. The agreement is excellent, confirming that time dilation occurs exactly as Einstein's theory predicts. Moreover, similar experiments have been done in particle accelerators, where muons and other unstable particles are accelerated to speeds very close to the speed of light. In these controlled conditions, physicists can measure particle lifetimes with extreme precision and verify that particles moving at high speeds live longer than the same particles at rest, with the lifetime extension matching the relativistic gamma factor perfectly. These accelerator experiments have tested time dilation at speeds up to 99.99% of light speed, where gamma factors can reach hundreds or thousands. And the agreement with relativity has been confirmed to incredible precision, to fractions of a percent or better. Perhaps the most ubiquitous proof of time dilation is one that billions of people use every day without realizing it: the Global Positioning System. GPS is a satellite-based navigation system that allows receivers on Earth to determine their position, velocity, and time by receiving signals from multiple satellites orbiting about 20,000 kilometers above the surface. The system works by measuring the time it takes for radio signals to travel from satellites to the receiver. Since radio signals travel at the speed of light, measuring the time delay tells you the distance to each satellite, and by combining distance measurements from at least 4 satellites, the receiver can calculate its position on Earth's surface with remarkable accuracy, typically to within a few meters or better. But this accuracy depends critically on extremely precise timing, and this is where relativity becomes essential. Each GPS satellite carries atomic clocks, typically cesium or rubidium clocks similar to those used in the Huffle-Keating experiment, but more advanced. These clocks must be synchronized with each other and with ground-based reference clocks to within a few nanoseconds, because a timing error of just 1 nanosecond corresponds to a position error of about 30 centimeters. Since light travels about 30 centimeters in 1 nanosecond. To achieve the system's design accuracy, the satellite clocks must stay synchronized to better than about 20 or 30 nanoseconds. But the satellites are moving at about 14,000 kilometers per hour relative to the Earth's surface, and they are in orbit at high altitude where gravitational fields are weaker than at the surface. Both of these factors affect the rate at which the satellite clocks tick due to relativistic effects. And if these effects were not corrected, GPS would quickly become useless. Let us calculate the magnitude of these effects. First, consider special relativistic time dilation from the satellite's velocity. At 14,000 kilometers per hour, or about 4 kilometers per second, the velocity gives a gamma factor of about 1 plus 8.3 times 10 to the minus 11th. This is very close to 1, but not quite, and the small deviation causes the satellite clocks to tick slower than ground clocks by about 7 microseconds per day due to their motion. This is special relativistic time dilation, the effect we have been discussing, and it causes the satellite clocks to lose 7 microseconds per day compared to clocks on the ground. Now, 7 microseconds might not sound like much, but remember that light travels 30 centimeters per nanosecond. So 7 microseconds is 7,000 nanoseconds, which would cause position errors of more than 2 kilometers per day. After just 1 day without correction, GPS would be off by kilometers, making it useless for navigation. But there is also a second effect, gravitational time dilation, which we will discuss in more detail in the next chapter. Because the satellites are high above Earth's surface, where gravity is weaker, their clocks actually tick faster than clocks on the ground by about 45 microseconds per day. This gravitational speed-up more than compensates for the velocity slowdown, so the net effect is that satellite clocks tick about 38 microseconds per day, faster than ground clocks when you combine both special and general relativistic effects. Specifically, the calculation gives negative 7.2 microseconds per day from velocity and positive 45.9 microseconds per day from gravitational potential, for a total of positive 38.7 microseconds per day that the satellite clocks gain. When GPS was being designed in the 1970s and 80s, some engineers were skeptical about whether relativistic corrections were really necessary. The effects seemed so small and relativity seemed so esoteric that there was debate about whether the system should include relativistic adjustments or whether they could be ignored. But the physicists insisted that the effects were real and significant, and eventually the decision was made to include the corrections. The satellite clocks are adjusted to tick at a slightly different rate before launch, so that once in orbit, experiencing both velocity and gravitational time dilation, they tick at the correct rate to stay synchronized with ground clocks. Additionally, the GPS receivers on the ground are programmed with the relativistic equations and continuously apply corrections as they calculate positions. Without these relativistic corrections, GPS would accumulate errors of about 10 kilometers per day, rendering the system completely useless for navigation. GPS is thus a practical, everyday demonstration that time dilation is real and must be accounted for in modern technology. Every time you use your smartphone to navigate, Every time you call a rideshare service, every time you check your location on a map app, you are relying on corrections for both special and general relativistic time dilation. The engineers who designed GPS had to take Einstein's equations seriously and build them into the system, because nature insists that time really does run at different rates for the moving satellites than for receivers on the ground. This is not abstract theory, but concrete engineering necessity. GPS proves billions of times per day that time dilation is as real as gravity, as solid as the ground beneath our feet, as undeniable as the fact that the sun rises in the east. It is simply how the universe works, and we have learned to work with it. Beyond these specific famous experiments, time dilation is confirmed constantly in modern physics research, particularly in particle accelerators, where physicists routinely accelerate particles to speeds very close to the speed of light. At facilities like the Large Hadron Collider at CERN on the border between Switzerland and France, protons are accelerated to 99.99999% of the speed of light, which gives a gamma factor of about 7,000. At this gamma factor, time dilation is extreme. A particle that would normally decay in 1 microsecond would instead live for 7,000 microseconds, or 7 milliseconds, in the laboratory frame due to time dilation. And this is exactly what is observed. Physicists can measure the lifetimes of high-speed particles with great precision using sophisticated detectors. And they find that particles moving at these extreme speeds live much longer than the same particles at rest, with the lifetime extension matching the relativistic gamma factor precisely. These particle physics measurements have tested special relativity to extraordinary precision, to better than 1 part in a billion in some cases, and no deviation from Einstein's predictions has ever been found. Time dilation is not an approximation or a first-order effect that breaks down with higher precision. It is exact, or at least as exact as we can measure, and it applies to all forms of timekeeping, from atomic oscillations to radioactive decay to biological aging. There is no physical process that escapes time dilation. Every clock, without exception, behaves in the way that relativity predicts. This universal applicability is what makes time dilation a statement about time itself, rather than about particular physical mechanisms. It is not that moving clocks are affected by some force or field that causes them to slow down. Rather, time itself is passing more slowly for moving objects, and all physical processes reflect this fundamental fact about the geometry of space-time. The experiments we have discussed, the Haffel-Keating atomic clock flights, the muon decay observations, the GPS system, and the particle accelerator measurements represent only a small fraction of the evidence for time dilation. There are many other experiments and observations that confirm relativity, including tests using spacecraft sent to other planets, observations of binary pulsar systems where neutron stars orbit each other at high speeds, measurements of particle decays in cosmic ray showers, and many more. Every experiment that has been performed to test time dilation has confirmed Einstein's predictions. No credible exception has ever been found. Time dilation is not a hypothesis or a speculation, but an established fact of nature, verified by more than a century of increasingly precise experiments, and incorporated into all of modern physics. What makes these experimental confirmations so powerful is that they span a wide range of conditions and methods. The Haffel-Keating experiment used macroscopic atomic clocks at relatively low velocities. The muon experiments use the natural radioactive decay of elementary particles at high velocities. GPS uses satellite motion and gravitational fields. Particle accelerators probe extreme velocities and short timescales. Each experiment tests time dilation in a different way with different systematic uncertainties, yet all confirm the same underlying theory. This convergence of evidence from diverse sources is the hallmark of a correct scientific theory. Relativity has passed every test that physicists have been able to devise, and with each passing year and each new experiment, our confidence that time dilation is real grows stronger. As you contemplate these experiments and their implications, as you consider that time itself is flexible and relative rather than absolute and universal, what questions arise in your mind? Are there aspects of time dilation you find particularly puzzling or particularly fascinating? Please share your thoughts in the comments below. Science progresses through questioning and discussion, and your perspectives contribute to the ongoing conversation about the nature of reality. And if you are enjoying this journey through the strange landscape of relativistic physics, if this content is providing both intellectual stimulation and a calming pathway towards sleep, please remember to like this video and subscribe to Science for Sleep. We have many more explorations planned, and your support makes this work possible. The time dilation we have discussed so far, arising from motion at high velocities, is only half the story. Einstein's special relativity of 1905 dealt with observers moving at constant velocity in the absence of gravitational fields. But the real universe is filled with gravity, from the gentle pull that keeps us on Earth's surface to the intense gravitational fields near neutron stars and black holes that warp spacetime into extreme configurations. Einstein spent the next 10 years after special relativity working on how to incorporate gravity into his relativistic framework. And the result was his general theory of relativity, published in 1915, which revealed that gravity itself is a manifestation of curved spacetime, and that gravitational fields cause time dilation just as velocity does. In fact, gravitational time dilation is more dramatic and easier to observe in many cases than velocity-based time dilation, and it leads to some of the most extreme and fascinating phenomena in the universe. The key insight that led Einstein to general relativity was what he called the equivalence principle, which states that gravitational acceleration is locally indistinguishable from any other kind of acceleration. Imagine you are in a closed room with no windows, unable to see outside. If you feel yourself pressed to the floor with the familiar sensation of weight, this could be because you are standing on Earth's surface experiencing gravitational attraction. Or it could be because your room is a spacecraft accelerating upward at 9.8 meters per second squared in deep space, far from any gravitating mass. Einstein realized that no experiment you could perform inside your closed room could distinguish between these two situations. The effects of gravity and the effects of acceleration are equivalent. This might seem like a trivial observation, but it has profound consequences when combined with special relativity. From special relativity, we know that accelerating reference frames experience time dilation. If a rocket is accelerating, the front of the rocket and the back of the rocket are at different points in space-time, and clocks at the front tick at a different rate than clocks at the back. By the equivalence principle, if acceleration causes time dilation, then gravity must also cause time dilation in exactly the same way. A clock lower in a gravitational field, closer to the source of gravity, should tick more slowly than a clock higher up where gravity is weaker. The effect is subtle for the weak gravitational fields we experience in daily life, but it is real and measurable, and Einstein predicted its exact magnitude. Clocks on Earth's surface tick more slowly than clocks on mountain tops or in orbit, and the difference is proportional to the difference in gravitational potential between the two locations. The first experimental test of gravitational time dilation was performed in 1959 by physicists Robert Pound and Glenn Rebka at Harvard University, in an experiment that has become famous as the Pound-Rebka experiment. They used the Mossbauer effect, a technique involving gamma rays emitted by radioactive iron atoms, to measure tiny frequency shifts caused by gravity. The experiment took place in the Jefferson Physical Laboratory Tower at Harvard, using gamma-ray sources and detectors placed at the top and bottom of a 22.5-meter tall tower. When a gamma-ray photon climbs upward in a gravitational field, it loses energy, which manifests as a decrease in its frequency, a gravitational redshift. When a photon falls downward, it gains energy and its frequency increases, a gravitational blueshift. The magnitude of this frequency shift is tiny for such a small height difference, only about 2.5 parts in 10 to the 15th, but the Mossbauer effect was sensitive enough to detect it. Pound and Rebka measured the frequency of gamma rays traveling up and down the tower and found that the frequencies shifted by exactly the amount predicted by general relativity. The downward traveling photons were blue shifted, having higher frequency at the bottom than at the top. The upward traveling photons were red shifted, having lower frequency at the top than at the bottom. Since photons are electromagnetic oscillations and can be thought of as clocks ticking at a particular frequency, this frequency shift is equivalent to time dilation. The gamma rays at the bottom of the tower were oscillating faster than the gamma rays at the top, which means that clocks at the bottom were ticking faster than clocks at the top from a certain perspective, or equivalently, time was passing more slowly at the bottom than at the top. The effect was minute, but it was real and matched Einstein's prediction with high precision. This was the first direct laboratory measurement of gravitational time dilation, confirming that gravity affects time just as special relativity had shown that velocity affects time. The magnitude of gravitational time dilation depends on the strength of the gravitational field, which in turn depends on the mass creating the field and the distance from that mass. Near Earth's surface, the effect is small but measurable. A clock at sea level ticks more slowly than a clock at high altitude by about 100 nanoseconds per day per kilometer of altitude difference. This might seem negligible, but remember that GPS satellites orbit at 20,000 kilometers altitude, So the gravitational time dilation accumulated over one day amounts to about 45 microseconds, as we discussed earlier. For stronger gravitational fields, the effect becomes more pronounced. On the surface of the Sun, clocks tick about 2 parts per million, slower than they would in deep space, far from any gravitating mass. On a white dwarf star, a dense stellar remnant with mass similar to the Sun compressed into an Earth-sized volume, clocks tick about 1 part in 10,000 slower. On a neutron star, even denser with perhaps 1.5 solar masses, compressed into a sphere only 20 kilometers in diameter, gravitational time dilation becomes dramatic, with surface clocks ticking perhaps 30% slower than clocks far from the star. The ultimate extreme of gravitational time dilation occurs near black holes, those mysterious objects where gravity is so strong that not even light can escape. A black hole is a region of space-time where gravity has become so intense that it has curved space-time to the breaking point, creating an event horizon, a boundary beyond which nothing can return. At the event horizon, gravitational time dilation becomes infinite. A clock falling toward the event horizon would appear to an outside observer to tick slower and slower, asymptotically approaching zero tick rate as it approached the horizon. From the outside observer's perspective, the clock would never actually reach the event horizon, but would appear to freeze in time, its light becoming increasingly red-shifted and dimmed until it faded from view. But from the perspective of someone falling with the clock, time would pass normally, and they would cross the event horizon in finite time without noticing anything special about that moment, though they would be doomed to fall further toward the singularity at the black hole's center, where physics as we know it breaks down. This extreme time dilation near black holes has practical consequences for any hypothetical space travelers who might venture near one. If you hovered at a distance just outside the event horizon of a large black hole and stayed there for what felt to you like 1 hour, when you returned to Earth, you might find that thousands or even millions of years had passed, depending on exactly how close you were to the horizon. This scenario was dramatized in the film Interstellar, which depicted astronauts visiting a planet orbiting close to a massive black hole, where time was so dilated that 1 hour on the planet equaled 7 years on Earth. This is not science fiction fantasy, but rather an accurate representation of how extreme gravitational time dilation works according to general relativity. The filmmakers consulted with physicist Kip Thorne to ensure the scientific accuracy of the time dilation effects. And while the specific numbers depend on the exact configuration of the black hole and orbit, the general phenomenon is real. Time really can pass at vastly different rates in different gravitational environments. Gravitational time dilation also affects light in a phenomenon called gravitational redshift. When light climbs out of a gravitational well, escaping from a massive object into weaker gravitational fields, it loses energy and its wavelength increases, shifting toward the red end of the spectrum. This is not the same as the Doppler redshift caused by motion, though it is analogous. Gravitational redshift is a direct consequence of time dilation, because the frequency of light is a measure of time, and time ticks slower in stronger gravitational fields. Light emitted from the surface of a massive object will be redshifted when observed far away where gravity is weaker. This effect can be observed in the light from the sun, where spectral lines are slightly redshifted compared to the same lines produced in laboratory sources on Earth. The effect is small for the sun, only about 2 parts per million, but it is measurable with modern spectrographs and matches the predictions of general relativity. For white dwarf stars, gravitational redshift is much larger and was historically one of the tests of general relativity. White dwarf light is redshifted by about 50 parts per million due to the star's strong surface gravity, and early measurements of this effect in the 1920s and 30s provided evidence for general relativity, though the observations were difficult and the interpretation was initially controversial. Modern measurements using spacecraft and high-precision spectroscopy have confirmed gravitational redshift to great accuracy, leaving no doubt that gravity affects light in exactly the way Einstein predicted. These observations of gravitational redshift are equivalent to observations of gravitational time dilation, because redshift and time dilation are two manifestations of the same underlying phenomenon, the warping of space-time by mass. The combination of velocity-based time dilation from special relativity and gravity-based time dilation from general relativity means that time in our universe is far more complex and varied than we ever imagined before Einstein. Every location in the universe has its own rate at which time passes, depending on the local gravitational field and on the motion of that location relative to others. There is no universal clock, no cosmic time standard that everyone can agree on. Time is local, relative, dependent on where you are and how you are moving. This is not a defect in our understanding or an approximation that will be corrected with better theories. It is how time actually works at the most fundamental level. The universe has no need for a universal time, because the laws of physics can be formulated entirely in terms of local measurements and space-time geometry. What matters is not the absolute time, but the relationships between events in space-time, the causal structure of which events can influence which other events. Interestingly, despite the complexity introduced by relativity, there are situations where observers can agree on certain measurements, even if they disagree on times and distances separately. The quantity called the space-time interval, which combines space and time measurements in a particular way, is the same for all observers, regardless of their motion or position in space-time. This interval is what remains invariant in relativity, replacing the invariant spatial distance of Euclidean geometry. The mathematics of general relativity describes how mass and energy curve space-time, changing the geometry and thus changing how distances and times are measured, but preserving certain deeper relationships that all observers agree on. This combination of relativity and invariance is the beauty of Einstein's theory, showing that behind the apparent chaos of different observers measuring different times and distances, there is an underlying order, a geometric structure to space-time that is the same for everyone. As we drift deeper into contemplation of these ideas, as the strangeness of gravitational time dilation settles into our minds, we can appreciate how far physics has taken us from the common sense world of our everyday experience. The ground beneath our feet, solid and stable, is actually sitting in a gravitational field that warps space-time and causes our clocks to tick slightly slower than they would if we were in orbit. Every step we take up a staircase brings us to where time passes infinitesimally faster. Every journey to higher ground is a journey to where time flows slightly more quickly. These effects are tiny in our daily lives, but they are real, and they grow to dramatic proportions in the extreme environments of neutron stars and black holes. Gravity is not just a force pulling things together, but a curvature of the very fabric of time and space, and time dilation is the signature of that curvature. The way we can measure and verify that space-time is not flat and absolute, but curved and relative. Time dilation, both from motion and from gravity, forces us to reconsider not just how time works, but what time is and what it means for events to happen in a particular order or to be simultaneous. The implications ripple through physics, philosophy, and our understanding of reality itself. If time is not universal and absolute, if different observers can legitimately disagree about the order of events or about which events are simultaneous, then our intuitive picture of the universe as having a definite past, present, and future that everyone shares must be wrong. The reality that emerges from relativity is stranger and more subtle, a reality where past, present, and future are not absolute categories, but depend on the observer, where the flow of time that seems so obvious and undeniable is revealed to be a local phenomenon rather than a cosmic truth. One of the most startling implications of special relativity is the relativity of simultaneity, which we touched on earlier but deserves deeper exploration. In Newtonian physics, if two events happen at the same time, they happen at the same time for all observers everywhere, regardless of their motion or position. There is a universal now extending across all of space. But in relativity, this universal now does not exist. Two events that are simultaneous in one reference frame are not simultaneous in another reference frame, moving relative to the first. This is not an illusion or a trick of measurement, but a fundamental feature of how space-time is structured. Events that are simultaneous for you might be separated in time for someone moving past you, and neither perspective is more correct than the other. Both are equally valid descriptions of reality from different reference frames. To understand how startling this is, consider what it means for distant events. Imagine there is a star 10 light-years away, and at this moment, from your perspective, that star explodes as a supernova. The light from the explosion will not reach Earth for 10 years, but in your reference frame, the explosion is happening now, simultaneous with you reading these words. But someone moving past Earth at high speed in a spacecraft would disagree. Due to the relativity of simultaneity from their reference frame, the supernova might have happened 10 years ago already, or might not happen for another 10 years, depending on the direction and speed of their motion. The difference can be years or decades for events separated by interstellar distances and observers moving at relativistic speeds. So when exactly did the supernova happen? The answer is that there is no absolute answer. It happened at different times in different reference frames, and all of those times are equally real and valid. This relativity of simultaneity means that the division of events into past, present, and future is not absolute, but depends on the observer. From your perspective right now, some events are in your past, meaning you could, in principle, have knowledge of them, because light or information from those events has had time to reach you. Other events are in your future, meaning they have not happened yet from your perspective. And other events are in your present, simultaneous with your current moment. But someone else moving relative to you would divide the same events differently into past, present, and future. Events that are in your future might be in their past. Events that are in your present might be in their past or future. The only events that all observers agree about are those that are causally connected, meaning light or information could travel between them. If event A could cause event B because there is enough time for a light signal to travel from A to B, then all observers agree on the temporal order of A and B. But if A and B are so far apart in space and close together in time that light could not travel from one to the other, then different observers can disagree about which happened first. This leads to the concept of light cones, a geometric way of thinking about causality in space-time. Imagine plotting time on one axis and space on another, creating a space-time diagram. Any event is a point on this diagram. The light cone of that event consists of all the points in space-time that could be reached from that event by light signals, both outgoing light into the future and incoming light from the past. The future light cone contains all events that could potentially be affected by the original event, because there is enough time for light or information to reach them. The past light cone contains all events that could potentially have affected the original event. Events outside the light cones are space-like separated, meaning they are too far apart in space and close in time for any causal influence to pass between them. And it is these space-like separated events for which different observers can disagree about temporal order. The existence of light cones and the restriction of causal influence to within them is why nothing can travel faster than light in relativity. If something could travel faster than light, it could carry information or causal influence outside the light cone, connecting events that are space-like separated. But because of the relativity of simultaneity, this would allow for situations where the cause could appear to happen after the effect in some reference frames, violating causality itself. You could, in principle, send a message to yourself in your own past, creating paradoxes like preventing your own birth, or receiving information about lottery numbers before they are drawn. The cosmic speed limit of light speed is not just a practical limitation, but a fundamental feature of how causality works in a relativistic universe. Going faster than light wouldn't just be difficult or require lots of energy. It would break the logical structure of cause and effect. These insights lead to different philosophical interpretations of time, debated by physicists and philosophers. One interpretation is called the block universe, or eternalism, which holds that all of space-time exists together as a four-dimensional block, with past, present, and future all equally real. From this perspective, time is just another dimension like space, and the passage of time is an illusion of human consciousness. The future already exists in the same sense that distant places in space already exist. We perceive time as flowing because our consciousness moves through the block universe, experiencing one slice after another, But the entire history of the universe, from beginning to end, is laid out eternally in the four-dimensional space-time structure. Einstein himself seemed to favor this view, writing to the family of his deceased friend Michel Besso that, for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. If time is relative, and there is no universal now, then it seems natural to conclude that all moments are equally real, and that our sense of time flowing is a feature of how we experience the world rather than a feature of the world itself. An alternative interpretation is presentism, which holds that only the present moment is real, that the past no longer exists, and the future does not yet exist. This view is more intuitive and matches our subjective experience of time, but it faces serious challenges from relativity. If different observers disagree about which events are present, then whose present is real? If there is no universal now, then what does it mean to say only the present exists? Presentism seems to require privileging one reference frame as somehow special, the frame that determines which moment is truly now. But relativity says there is no such special frame. Various sophisticated versions of presentism have been proposed to try to reconcile this view with relativity, but the tension remains, and many physicists and philosophers find presentism difficult to maintain in light of relativistic physics. A third interpretation is the growing block universe, which holds that the past and present are real, but the future is not yet real. Time is the process by which new moments come into existence, with the present being the leading edge of reality as it grows into the future. This view tries to preserve the reality of time's flow and the distinction between past and future, while acknowledging that the past is fixed and real. But like presentism, the growing block view faces challenges from relativity's lack of a universal present. If different observers disagree about which events have already happened, then it is unclear what it means for the block to have a definite growing edge. Nevertheless, some philosophers find this view attractive because it seems to preserve something important about our experience of time having a direction, and of the future being open and undetermined in a way the past is not. These philosophical questions about the nature of time are not just abstract speculation, but are motivated by the real physics of relativity. Time dilation forces us to take seriously the possibility that time is not what we thought it was, that the flowing river of time that seems so fundamental to experience might be a construct of consciousness, rather than a feature of external reality. This does not mean that time is unreal, or that physics denies the existence of temporal order. Events still have causal relationships. Earlier events can affect later events, but not vice versa. And there is an objective structure to space-time that all observers can agree on, even if they describe it differently in their local coordinates. But the simple picture of time as a universal cosmic clock ticking away the moments one by one, creating a universal present that sweeps across the universe like a wave, that picture is demonstrably wrong. Time is more subtle, more geometric, more relative than that. Time dilation also enables a form of time travel, specifically travel into the future. If you could accelerate to very high speed, close to the speed of light, and travel for what feels to you like a few years before decelerating and returning, you would find that much more time had passed on Earth due to time dilation. This is not hypothetical, but follows directly from the confirmed physics of relativity. You would have traveled into Earth's future, aging only a few years, while decades or centuries passed on Earth. This is the same effect as the twin paradox, and it is a real possibility if we could ever develop propulsion systems capable of accelerating spacecraft to relativistic speeds. No law of physics prevents this forward time travel. It is merely an engineering challenge, an extraordinarily difficult one, but not fundamentally impossible. Traveling backward in time is far more problematic. Most solutions to Einstein's equations that allow backward time travel involve exotic configurations of space-time, like rotating black holes or wormholes, traversable shortcuts through space-time that could, in principle, connect different times as well as different places. But all of these solutions require exotic matter with negative energy density, something that has never been observed and may not be possible in our universe. They also typically lead to causality paradoxes, situations where you could go back and prevent your own time travel or create other logical contradictions. Most physicists suspect that nature has some mechanism, perhaps at the quantum level, that prevents backward time travel and preserves causality. The chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics conspire to prevent the formation of closed time-like curves that would allow backward time travel. This remains an open question, but the consensus is that while forward time travel via time dilation is completely allowed and verified, backward time travel is at best highly constrained and may be fundamentally impossible. The reality we inhabit, as revealed by time dilation and relativity, is one where time is woven together with space into a unified fabric, where the rate at which time passes depends on motion and gravity, where simultaneity is relative and the division into past, present and future is observer-dependent. This is not the comfortable Newtonian universe of our intuitions, but a stranger, richer, more subtle reality. And remarkably, we have learned all this not through speculation, but through careful observation and experiment, through building atomic clocks and flying them around the world, through observing muons from cosmic rays, through designing GPS systems that must account for relativistic effects, through measuring the light from distant stars and the behavior of particles in accelerators. The universe has taught us that time is relative, and we have listened and learned and built technologies that rely on this knowledge. We live in a reality shaped by relativistic physics, whether we realize it or not. What aspects of time dilation fascinate you most? The philosophical implications about the nature of reality, the possibility of traveling to the future, the strange fact that two observers can disagree about the order of events. Please share your thoughts in the comments below. These questions have puzzled and inspired physicists and philosophers for over a century, and the conversation continues as we probe deeper into the nature of time and space. Your perspectives and questions are valuable contributions to this ongoing exploration of reality. Time dilation is not just a curiosity of physics laboratories or a complication for GPS engineers. It is a fundamental aspect of how the universe works, affecting phenomena from the smallest scales of quantum mechanics to the largest scales of cosmology. Throughout the cosmos, wherever there is motion or gravity, time dilation is at work, shaping the behavior of particles, stars, galaxies, and the structure of space-time itself. Let us take a tour through the universe and see how time dilation manifests in various astronomical and physical contexts, from rapidly spinning pulsars to the expansion of the universe itself. Pulsars are among the most fascinating objects that demonstrate relativistic effects, including time dilation. A pulsar is a rapidly rotating neutron star, the collapsed core of a massive star that exploded as a supernova. Neutron stars are extraordinarily dense, with about 1.5 times the mass of the Sun compressed into a sphere only about 20 kilometers in diameter. This makes them dense enough that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravitational field at the surface of a neutron star is immense, about 100 billion times stronger than Earth's surface gravity, and this creates significant gravitational time dilation. Clocks on a neutron star surface would tick about 30% slower than clocks far from the star, a substantial effect observable in the light emitted by the star. Some neutron stars rotate extremely rapidly, spinning hundreds of times per second, with their surfaces moving at significant fractions of the speed of light. The fastest known pulsar, designated PSRJ 1748-2446 AD, rotates 716 times per second, meaning its equator is moving at about 24% of light speed. At this velocity, special relativistic time dilation becomes significant, in addition to the gravitational time dilation from the star's mass. For matter at the pulsar's equator, time is dilated both by motion and by gravity, running substantially slower than time far from the star. The combination of these effects influences the pulsar structure and the emission of radiation that we detect as regular pulses, the lighthouse-like beams that sweep across Earth as the pulsar rotates. Binary pulsar systems, where two neutron stars orbit each other, provide some of the most precise tests of general relativity, including time dilation effects. The first binary pulsar, PSRB 1913+16, was discovered in 1974 by astronomers Russell Hulse and Joseph Taylor, who later won the Nobel Prize for this discovery and the subsequent verification of general relativity it enabled. In this system, two neutron stars orbit each other every 8 hours, with orbital velocities reaching about 400 kilometers per second. At these speeds, both neutron stars experience significant time dilation, and the system's orbital parameters change over time in ways predicted by general relativity. One particular prediction is that the system should lose energy by emitting gravitational waves, ripples in space-time that carry energy away from the system. This energy loss should cause the orbit to slowly shrink, with the orbital period decreasing by about 76 microseconds per year. Hulse and Taylor monitored the binary pulsar for decades, using the extremely regular pulses from one of the neutron stars as a cosmic clock to measure the orbital period with exquisite precision. They found that the orbit was indeed shrinking at exactly the rate predicted by general relativity, including all the time dilation and other relativistic effects. The agreement between theory and observation was so precise, matching to better than 1%, that it provided compelling indirect evidence for gravitational waves decades before their direct detection in 2015 by LIGO. And the binary pulsar system is a natural laboratory for testing relativity in strong gravitational fields and at high velocities, conditions far beyond anything we can create on Earth. And it confirms that time dilation and all other relativistic effects are accurately described by Einstein's equations, even in these extreme environments. The direct detection of gravitational waves by LIGO and subsequent observatories has opened a new window on relativistic phenomena, including time dilation. Gravitational waves are produced by accelerating masses, particularly by compact objects like neutron stars and black holes orbiting each other and eventually merging. These waves travel through space-time at the speed of light, stretching and squeezing space as they pass. When gravitational waves pass through the Earth, they cause tiny distortions in space-time that LIGO can detect by precisely measuring the distance between mirrors suspended in vacuum chambers using laser interferometry. The first detected gravitational wave signal came from two black holes, each about 30 times the mass of the Sun, spiraling together and merging into a single larger black hole about 1.3 billion light-years away. The black holes in this system were orbiting at significant fractions of light speed before they merged, and they were moving through extremely curved space-time near their mutual event horizons, where gravitational time dilation is extreme. The gravitational wave signal encodes information about the masses, spins, and orbital dynamics of the black holes, and analyzing this signal allows physicists to test general relativity in the strong field regime, where space-time curvature is enormous. All observations have confirmed general relativity to high precision, showing that the theory correctly describes even the most violent and extreme gravitational events in the universe. Time dilation is an integral part of this description, affecting how the black holes orbit, how they emit gravitational waves, and how those waves propagate through space-time to reach our detectors. Time dilation also plays a role in cosmology, the study of the universe as a whole. The universe is expanding, meaning that distant galaxies are receding from us, and the space between galaxies is growing over time. This expansion causes cosmological redshift, where light from distant galaxies is stretched to longer wavelengths and lower frequencies as it travels through expanding space. While cosmological redshift is not exactly the same as gravitational redshift or Doppler redshift, it is related to time dilation in the sense that distant galaxies exist at earlier times in the universe's history, and there is a relationship between their recession velocity and the rate at which time passes in their reference frame versus ours. For very distant galaxies, billions of light-years away, we are seeing them as they were billions of years ago, when the universe was younger and denser, and the processes occurring in those galaxies appear to be time-dilated from our perspective. This cosmological time dilation can be observed in the light curves of distant supernovae, exploding stars that serve as standard candles for measuring cosmic distances. Supernovae have characteristic brightening and dimming patterns over time, with a particular type called Type 1. a supernovae having very consistent behavior that makes them useful for cosmology. When astronomers observe distant Type 1a supernovae billions of light-years away, they find that the light curves are stretched out in time compared to nearby supernovae. A supernova that would brighten and fade over a few weeks in the local universe appears to take longer when at high redshift, and the amount of time stretching is proportional to the redshift, exactly as expected from cosmological time dilation. This effect is yet another confirmation that time is relative and is affected by the expansion of space-time itself. At the smaller scales, time dilation affects quantum mechanics and particle physics in ways that are important for understanding the fundamental forces and particles. The standard model of particle physics describes how elementary particles interact through electromagnetic, weak, and strong forces, and many of these interactions involve particles that exist only briefly before decaying into other particles. The lifetimes of these unstable particles are affected by time dilation when the particles are moving at high speeds, which they often are in particle colliders and cosmic ray showers. Physicists must account for time dilation when calculating the production rates and decay patterns of particles, and the agreement between theoretical predictions and experimental observations provides constant verification that time dilation is correctly incorporated into our fundamental theories. One particularly interesting example involves the Higgs boson, the particle associated with the Higgs field that gives mass to other fundamental particles. The Higgs boson was discovered at CERN in 2012 and has a lifetime of about 10 to the minus 22 seconds, extraordinarily brief even by particle physics standards. When Higgs bosons are produced in high-energy collisions at the Large Hadron Collider, they're often moving at speeds close to light speed, and their lifetimes are extended by time dilation. Even with this time dilation, they travel only a tiny fraction of a millimeter before decaying. But time dilation is part of the calculation of where and how they decay and what decay products they produce. The entire enterprise of particle physics rests on relativistic quantum field theory, which seamlessly incorporates both quantum mechanics and relativity, including time dilation, and the extraordinary agreement between this theory and experiment is one of the great triumphs of 20th century physics. Looking to the future, time dilation will be crucial for any attempt at interstellar travel. The distances between stars are enormous, with even the nearest star system, Alpha Centauri, being about 4.4 light-years away. At current spacecraft speeds, a journey to Alpha Centauri would take tens of thousands of years, far longer than human lifespans or even the duration of human civilizations. But if we could somehow accelerate a spacecraft to a significant fraction of light speed, time dilation would work in the traveler's favor. A spacecraft traveling at 99% of light speed would experience a gamma factor of about 7, meaning that a journey of 50 light-years, according to Earth's clocks, would take only about 7 years, according to the traveler's clocks. At 99.9% of light speed, gamma is about 22, and a 50 light-year journey would take only about 2.3 years of traveler time. This is still many times longer than the travelers would measure because they would be experiencing much less time than Earth observers measure. But It makes interstellar exploration conceivable within human lifetimes from the traveler's perspective. Of course, accelerating to such speeds presents enormous challenges. The energy required to accelerate even a small spacecraft to relativistic speeds is immense, far beyond any propulsion technology we currently possess. The spacecraft would need to carry fuel or use some external energy source like solar sails or beam propulsion, and would need shielding to protect against collisions with interstellar gas and dust that would become lethal at such speeds. But time dilation means that relativistic space travel is not fundamentally impossible, merely extraordinarily difficult. If future civilizations developed the technology for relativistic travel, they could explore the galaxy with travelers aging only years or decades while journeying across hundreds of light years. They would return to find that centuries had passed in their homeworlds due to time dilation, effectively traveling into the future, but they could visit distant stars within their natural lifetimes. Generation ships, hypothetical spacecraft designed to travel for centuries with multiple generations of crew born, living and dying aboard, would experience less dramatic time dilation if they traveled at lower speeds. A generation ship traveling at 10% of light speed would have a gamma factor of only about 1.005. meaning time dilation would be negligible and the journey would take about the same time for travelers and Earth observers. But if such ships could achieve higher speeds, say 50% of light speed, gamma would be about 1.15, and a century-long journey according to Earth would take only about 87 years according to the ship's clocks. This modest time dilation might not seem like much, but it would mean that fewer generations would be needed aboard the ship, at slightly improving the odds of mission success. Time dilation is thus a factor in all speculative designs for interstellar travel, affecting mission planning and the experience of travelers who venture into the cosmic ocean. Throughout all these examples, from neutron stars to supernovae to particle colliders to interstellar travel concepts, time dilation is not an inconvenient correction to apply to calculations, but rather a fundamental aspect of how the universe operates. It affects every physical process, every clock, every measurement of time. The universe has no preferred reference frame, no cosmic clock ticking away absolute time. Instead, time is local and relative, different for every observer depending on their motion and position in gravitational fields. This is not a flaw or complication, but is the natural way time works when we recognize that space and time are woven together into space-time, and that the speed of light is the cosmic speed limit that all observers measure as the same. Time dilation is as real as gravity, as concrete as the ticking of the watch on your wrist, as undeniable as the navigation instructions from your phone. It is simply how our universe is structured at the most basic level. The story of time dilation is not just a tale of abstract physics and esoteric experiments, but has practical consequences for the modern technological world we inhabit. Many of the technologies we rely on daily were designed with an understanding of relativity, and would not function properly without corrections for time dilation. This is particularly striking because relativity is often presented as being relevant only for exotic phenomena like black holes or near light speed travel. Yet it affects systems that billions of people use every day. Understanding how time dilation has been incorporated into modern technology gives us a concrete appreciation for how physics shapes our lives in ways we rarely notice or think about. Particle physics research, conducted at facilities around the world, including CERN, Fermilab, and many others, depends entirely on relativistic physics, including time dilation. When physicists accelerate particles to speeds approaching the speed of light and collide them to probe the fundamental structure of matter, every aspect of the experiment is governed by relativistic equations, the energies of the particles, on the curvature of their paths in magnetic fields, their decay lifetimes, their collision probabilities. All of these depend on relativistic effects. The data analysis software that reconstructs particle trajectories from detector signals incorporates relativistic kinematics, and the theoretical predictions that physicists compare to experimental results are calculated using relativistic quantum field theory. Without understanding time dilation and other relativistic effects, particle physics would be impossible. We would not have discovered the Higgs boson, the top quark, or any of the other fundamental particles found in recent decades. Our entire understanding of the universe at its smaller scales rests on the foundation of relativity. Medical imaging techniques, including PET scans, positron emission tomography, also rely on particle physics and thus indirectly on relativistic effects. PET scans work by injecting a patient with a radioactive tracer that emits positrons, the antimatter counterparts of electrons. When a positron encounters an electron, they annihilate, converting their mass into energy in the form of gamma-ray photons. By detecting these photons and analyzing their directions and timings, medical scanners can reconstruct images of metabolic activity inside the body, helping diagnose cancer, heart disease, and neurological conditions. The physics of positron emission and annihilation is described by relativistic quantum field theory, and the decay rates of the radioactive tracers are affected by time dilation if the tracers are moving at high speeds, though this effect is negligible for the speeds involved in biological systems. More directly, the production of medical isotopes often involves particle accelerators where relativistic effects are important. So even medicine, which seems far removed from Einstein's theories, is touched by relativity. In research laboratories around the world, atomic clocks are being developed that are so precise they can measure gravitational time dilation over height differences of just a few centimeters. These optical atomic clocks use transitions in atoms like strontium or ytterbium that oscillate at optical frequencies much higher than the microwave frequencies used in traditional cesium clocks, allowing for greater precision. The best optical atomic clocks can now measure time with an uncertainty of less than 1 part in 10 to the 18th, which means they would gain or lose less than 1 second over the age of the universe. At this precision, you can actually measure the difference in time flow between your head and your feet, due to the difference in gravitational potential. A clock at your head, about 2 meters higher than your feet, ticks about 2 parts in 10 to the 16th faster than a clock at your feet. This is an absurdly small effect, but modern clocks can measure it, demonstrating that gravitational time dilation is not just a phenomenon of planets and stars, but is present everywhere, affecting everything down to the most minute level. These ultra-precise clocks have applications beyond fundamental physics. They could be used for geodesy, the measurement of Earth's shape and gravitational field, with precision far beyond current surveys. By placing atomic clocks at different locations and measuring the tiny differences in their tick rates due to local variations in Earth's gravitational field, scientists could map the geoid, the shape of Earth's gravitational equipotential surface, with unprecedented accuracy. This has applications for understanding ocean currents, tectonic motions, magma movements beneath volcanoes, and many other geophysical processes. Time dilation thus becomes a tool for Earth science, connecting the abstract physics of space-time curvature to practical questions about how our planet works. As technology continues to advance, our need to account for relativistic effects will only increase. Future space missions to the outer solar system, or even to other stars, will need to carefully consider time dilation in their designs and operations. Communications with spacecraft experiencing significant time dilation would need to account for the fact that their clocks run at different rates than Earth clocks. Autonomous spacecraft making decisions in real time would need to coordinate with mission control on Earth despite the time dilation effects and light delay. If we ever establish permanent settlements on other planets or moons with different gravitational fields, time will literally pass at different rates for settlers than for people on Earth. And this will affect everything from communications to scheduling to the synchronization of databases and transactions. As this journey through the nature of time comes to its conclusion, as your eyelids grow heavy and sleep approaches, I want to thank you for traveling with me through these ideas. Thank you for staying curious, for being willing to consider that the universe might be stranger than it seems, for engaging with concepts that challenge intuition but are supported by evidence. If you have found this exploration valuable, if it has changed how you think about time, or inspired new questions, or simply provided a peaceful path toward sleep, please consider subscribing to Science for Sleep. We create these detailed explorations because we believe that learning and sleep are compatible, that the mind can be both stimulated and calmed, that wonder and rest can coexist. Before you close your eyes and surrender to sleep, one final thought. The next time you look at a clock, any clock, remember that it is measuring something flexible and relative, something that Einstein revealed to be woven together with space into a unified space-time fabric. Remember that time itself is not absolute, but depends on motion and gravity. Remember that the simple act of checking the time connects you to one of the deepest insights in all of physics. And remember that we live in a universe that is stranger, more subtle, more interconnected than common sense suggests. A universe that reveals its secrets to patient observation and careful thought. A universe that we are privileged to explore and understand. Sleep well. Dream of time flowing and bending. Of clocks ticking at different rates. Of light always traveling at the same speed regardless of how you chase it. Of the beautiful equations that describe it all. And know that when you wake, time will have passed. Your clocks will have ticked forward, and you will be ever so slightly further into the future, having time traveled through sleep as we all do every night, experiencing time's passage in the most direct and personal way possible. The universe awaits tomorrow with more mysteries to explore, more questions to ponder, more evidence to gather. But for now, rest. Let the strangeness and beauty of time dilation accompany you into dreams. And until we meet again for another journey through the wonders of science, good night.